All right. And share the, sorry. Okay, can you hear my, can you see my screen already? Yeah, okay, so. All right, so the last section of this chapter is the method of Lagrange multipliers. Okay, so let's me just start with the, um, okay, so this applies to Western Asia, but doesn't matter. All right, so two kind of extreme problem that we have from this sections. Let me show you the, where is, all right, this one from the, okay, so yesterday we compute use with the help of Maple of the problem 28. Okay, and then you see that problem 29 here. Determine maximum value of functions subject to the constraint of this one. Okay, so we need to maximize or minimize the function, but you have a constraint also here. Same thing with 30. Maximum value of product of three numbers. So you have to uh, maximize x, y, z. If x, y, z satisfies this one. Okay. So you have a what we call a, this one here. So, okay. So this is a extreme value problem. So no constraint, without constraint. So just maximize or minimize something. So straightforward. Okay. And you have a uh, finding extreme, but you have a constraint to satisfy. For example, this one, you need to maximize this one, x squared plus y squared, but with a constraint, say conditions that xy minus 3 must be 0. Okay. So, the function to be minimized or maximized is called objective functions. Okay, so that's the what they call what we need to maximize or minimize, and then the condition is called constraint. So this is the constraint minimization or maximization, optimizations. All right, and we take a note a little bit that the uh, extreme problems in real problems almost always like this. So you have a constraint. Okay, so generally you have to maximize or minimize a function, the objective functions, with a constraint G. So maximize F, the constraint is G. G equals something. Okay. So how we see this geometrically? So suppose F describe a, if it's two variable, okay. So Z describe a surface, okay, while the constraint Gxy equals K, that is defined in what we call level curves. Okay. Okay, so if we able to parameterize the curve, this level curves, then you should of try to maximize uh, a function on that curve. Okay, that one. So find the highest point or the lowest point. So highest point or lowest point of a path on surface. See this one here. So you have a surface as a objective functions. So this paraboloid, okay, and you have this curve G equals K. So these level curves on the plane here, right? So if you project this curves onto the surface, you see this a path here on the surface along the surface. Okay, so along these curves on the surface, you would like to find the highest point and the lowest point. Okay, so that's what it means geometrically of a what you call the extreme constraint extreme. Okay, so with this one, if we look from the top, okay, this is the for example, this is the level curve of this one. So the level curves of the paraboloid is just a circles, and the level curve of G looks like this one, like this one. Okay. So from the top, you see this one here. Okay. So in this case, you see that going outside, the value is getting bigger. See, because that's the paraboloid. So we see from here, just look, uh, the outermost curve, outermost part of the curve, that's the how would be the highest point. So let's see here. This is not the highest would be here or here, here, this point or this point, but it turns out to be this one here. So according to this should be the highest. So that's how we see that geometrically. So we need to compute this point. Okay. So the geometric identification of that maximum or minimum is that the constraint, the curve of the constraint, only touch the level curve of this one here. Okay, so we need to find the largest or the smallest c. Okay, so if we here see, because this going outside is getting bigger, so then we need to find the outermost part of the curves. Okay, so clearly this is the outermost part. This is not the outermost because it's keep going getting larger. So going outside. Now the point is that we need to find something where the curves touch the level curve. So touch circles, not crossing circles. So that's the idea. Not crossing the circles, but touch circles, only touch. So circles can be replaced by level curves. Okay. Okay. So what does it mean by uh, touching here? This is what we call the touching. So the at that point, the curves, the constraint curves, uh, of course, that must intersect the level curves, okay, but tangentially. That means tangential here, for example, here. So this is the point where this constraint touch a level curves. See, okay. So this one, now this one's crossing, this one crossing, 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 crossing. Only this one touch. And so that's the point. Okay. So we need to find how to find this point here. Okay. So you see, tangentially. That's the idea. Okay. So this is tangential means that they have the same normal. Okay. So the level curves, the constraint curves, the G and F must have a same normal. Well, not really the same, but one is a scalar multiply of the other. Okay, so that's one. The last one is the normal factor of the curve, the level curves, and the normal factor of the constraint at that point must be a multiple of each other. So for example, is we know that the level curves, sorry, the normal factor is the gradient. Right? But that's from the last, well, section 7 or something. So you see the gradient f at the point P naught, that's the point that we are looking for, okay, is a multiple lambda times the gradient of G. Okay, so that's the criteria. All right, so this is what you call a Lagrange multiplier. So to maximize or minimize f, a function f, with a constraint G equals 0, say, we need to solve this one. Okay, so solve the gradient f equals lambda times gradient p, and this was, of course, g of p equals 0. So this is the constraint. Okay, so the point P which satisfy this one called the critical point of the constraint extreme problem. Okay, and the value lambda is a scalar, so this is a number. Okay, this is called the Lagrange multiplier. Why this? Because this multiply the gradient. Okay. So let's see, this is the an example. So to find the maximum, find the extreme function of f. Okay, doesn't say whether it is a max or min, right? But on the ellipse. Yes. So this is the objective. This is the constraint. So what we do with this? Okay, so this is constraint. So you put this equals 0. Okay. So let's put it equals 0. Let's put this p equals 0. Okay, so we define d equals 0. Right. So we try to solve this one in gradient f equals multiple of gradient of g. Okay, so we compute this gradient of f is just negative 2x and 2y here, while gradient of g is this So we have x over 2 and 2y. Okay, so we need to make them equal. Okay, so this negative 2x must equal to lambda times x over 2. I think I made a mistake here because this should be equal to this one. That should be equal to this one. Okay. Okay, so we have this is not 2x, but x over 2. Okay, and this one, 2y equals lambda times 2y. Okay, and we solve this. Okay. Uh, I think I made a mistake here. Let's do this one here. Okay, so that should be derivative with respect to x means negative 2x plus lambda times derivative of this. So x over twice x over 2. And second must be respect to y. So with 2y equals lambda times this also 2y. Okay. And then the third, of course, you have to cut it off this one. Okay, so we multiply this by 4, so x squared plus 4y squared equals 1. So equals 4. Okay. From 2. From 2 tells you that, well, this is y, this is 2y, so this lambda must be 1. I think there's a mistake here. If lambda equals 1, then there's no way. Hmm. Okay. Main stop here and then try to reset the the slide. Okay, so let me just share again. Right. Uh, I made mistake here in this case. I think somehow the x and y switch over. The x should be y and y should be x here. So uh, let's uh, let's just do this for a while, and we'll see. We'll switch the x and y later on. Okay, suppose we need to solve this one here. Okay, we solve this one. So please do it carefully. So we need to solve 1 to 3. Okay. So in solving 1 to 3, okay, so see, from 3, for example, x and y cannot be equal to 0. See, you see x squared plus 4y squared must be 4. So cannot be x and y equals 0. Okay. So from 1 here, so this tells you that lambda must be -1. If uh, if x not 0. If x is 0, then lambda can be anything, right? But if x not 0, then lambda must be -1. Okay. So if lambda is not 0, to this -1, from 2, uh, we get y must be 0. Okay. And we proceed by 3. Okay. So, so that's why if y equals 0, then x must be plus minus 2. Okay. So we get a critical point 2.0 and a negative 2.0. Okay. While when y is not 0, if y is not 0, here, so lambda must be 1/4 from 2. Okay. So from 1, if that's not 0, then lambda must be 0. So in this case, y must be plus minus 1. So we get at this point 2 points. So 4 points. 2, 0, -2, 0, 0, 1, 0, and -1. Okay, so we need to find. All right, so at this point, the value is -4, -1. So in this case, the value, the maximum, the minimum would be -4. The maximum would be 1. Okay. The nice thing about Lagrange multiplier method is can be used for uh, variable more than 2. So 2, 3, 4 doesn't matter. Uh, that's why the Lagrange multiplier is useful because we often have more than 2 variables. Okay. And this one here. So here we have 4 points, so you can compare. The highest one would be the maximum, and the lowest one would be the minimum. But in case you have only one point, so you're not sure whether it is max or min. So you need to make a comparison. Okay, so just find another point on the curve as a comparison. All right, second example. You have this. You have to minimize a function, or objective function, three variables, you see, x, y, z. So we cannot even draw the picture, the graph with this. Okay. And the constraint of is g equals 0 here. Okay, so we need to compute the gradient. Because it's linear, so the gradient is just 3, 2, 1, right? The gradient of g is 18x, 8y, and negative 1. Okay. So this tells you already 18x lambda times 18x equals 3, for example. So we need 4 equations. So 1, 2, 3, 4. 3 coming from the gradient, and 1 coming from the constraint. So we need to solve x, y, z, and lambda. Okay, so you need, well, we put another one more variable, which is lambda. So we can solve it. Right? How to solve this? Let's, from 3, this lambda is negative 1 already. Substitute this to 1 and 2, you get x, negative 1, 6, y is negative 1, 4. Substitute to fourth, you get z equals 1/2. Okay, so you get this one here. Okay, only 1 point. So that's reason why you're not sure from this point whether what you get is maximum or minimum. The value is 9. So we need to find another point which lies on the curve, on the level curves, G constraint. All right, so let's find. In this case, just find something easy. For example, in this case would be, well, you put x0, y0, and the z equals 0. So then 4 is satisfied. And find the value of its origin. So 5, which is larger than 9.5. Okay. All right. Because so from here we conclude that, well, this 9.5 must be minimum, cannot be a maximum. Okay. Otherwise, they should be bigger than 5. Okay. So obviously, just note, more than 2 variables, you just cannot draw the picture. Okay, so that's the idea. So how we do this for 2 extremes? Sorry, 2 constraints. MA. Okay, so the Lagrange equation for this is gradient of f equals lambda times gradient of g times a mu times gradient of h, and you solve this one. Okay, so for example, here, just one example. So the objective function is, well, this is equal sign. We have 2 conditions. So you just need to find the Lagrange equations. Just skip this. Just one more example from the give you one more example from the textbook. That's how you find it. Okay, so let's see. Let's do another problem, but the express formulated as the constraint minimization. So we need to find maximum and minimum of this function, objective functions, okay, on the set like this. So you see, if you picture this one, so in this case, z equals this one. So you see this is x squared and y squared have same sign, right? So this should be a paraboloid, opens down. So, okay, because that's negative. So on the set, see that the S now has a boundaries. Okay, so the boundaries equals to 1. So that means it's a circle of radius 1. Okay, so we do two things. For the interior means that x squared plus y squared less than 1. So interior of the circle. Okay, and for the circle, let's do this. Okay, so this will satisfy this, and then we need to uh, find the critical point. Use the branch. Okay, and then compare uh, the maximum minimum we get from 1 and 2. Sorry, 1 and 3. Okay, so let's just do one example. Um, all right. Let's just do this one more example. Just do this one. So let's see. This S would be this circle. Okay, so this S, and this is the interior. So this is the interior. And the circle. Okay, so say this is 1 and this is 2. Okay, for 1, this is interior. Okay, so let's do um, uh, let's just do this one here. Oh, I think so this is extreme without problems. Okay, so let's compute that one. Okay. Our interior. So we need to find the maximum or minimum for this one. In this case, would be a plane. Uh, so this is z equals x plus y is a plane. Plane on three space. In three space. Okay. So it looks like uh, just a plane like this. So therefore, there's no minimum or maximum. Okay. Okay. So we need to find the uh, one in the interior. Okay. So with the with bound. So maximize or minimize 10 plus x plus y with constraint um, what is this? Okay. Okay, so this is our G. This is our F. Okay. All right. So check this one. All right. So from we need to solve this one here. Equals lambda times okay. Find lambda and p. Okay. So first, respect to x, derivative respect to x. Let's see. P is just one. 1 equals lambda times gradient of so partial of this one. So 2x. Second is just another one lambda times this is not 2y. Okay, and the third you need to solve that x squared with y squared equals 1. Okay. So it's b from 1 lambda equals to um, all right, no, from 1 and 2. Let's solve this one. So lambda times 2x equals 1 equals lambda times 2y. Okay. So if you assume lambda non-zero, you can cancel lambda and you get x equals y. Okay. So let's proceed with this one with these assumptions. Okay. If x equals y, then from 3 you get, you substitute. That means 2x squared equals 1. So x is plus minus 1/2 squared, 1/2 or square root of 2. Okay, so that equals y. Okay, so then this is what we get. There's 2 points. Uh, 1, 1, and negative there. Okay. Now what happens if lambda equals 0? If lambda equals 0, so is it possible lambda equals 0? If lambda equals 0, then 1 equals from 1. So you cannot be in case. Okay, so this one is no. Okay, so we have these two solutions. Okay, and then so we check now. F of 1/2 square root of 2, that is 10. Okay, so 10 plus square root of 2 at negative. Okay, so this 10 minus. Okay, so this is larger. Then in this case, on the boundary, the max would be, sorry, at and when at this point. That's max min. All right, this is the max min on the boundary. Okay, so since the interior, there is no max-min, on the interior, then max-min only occurs at the boundary. Then max-min occurs only at the boundary. Okay, so that's why there's uh, the maximum is so this is the conclusions, right? Okay, so this is the Lagrange multiplier method. So so we're done with the chapter 12. Okay, so and I'll let you do the exercise with me. Kemal. Okay, so I will see you next week. I'll stop the share and Kemal will take over this one. Let's see, where is YouTube? All right, so please take over, Kemal. So I'll see you then next week. Thank you.
Thank you very much, Pak Yudi. All right, let's begin our tutorial. Good morning, everyone. And our tutorial sheet is still the same with the last week. It is chapter 12 tutorial. If you have any question, please let me know which question do you want to ask.
Kak, I want to ask a question, Kak.
Okay.
Can you explain from the tutorial question number 26, Kak?
26. Okay, let me see. All right. Taylor polynomial, right? Okay, let me see. Because actually I forgot the second order Taylor polynomial in here. Let me see the formula for that. Second order Taylor polynomial. Okay, I cannot there are no Taylor polynomial in this book. Just wait a little bit. Doesn't seem there is any second order Taylor polynomial, so let me search it a little bit. Second order Taylor polynomial multivariable. See? For the first order, but for the second order, okay, it's like that. Okay, so this is the number 26. So you know, Taylor polynomial in one variable function is like this for fx. So if if f has only one variable as its input, then its Taylor polynomial or its Taylor expansion near x equals a is fx equals fa plus f prime a x minus a plus f double prime a over 2 times x minus a squared, and so on, right? So we also have the Taylor polynomial for multivariable function. For two variables, its Taylor expansion near the point xy equals ab is kind of similar with the one variable version. So fxy will be fab plus I think it is fx ab times x minus a plus fy ab times y minus b plus fxx ab over 2 times x minus a squared plus fxy ab times x minus a times y minus b plus fyy ab over 2 times y minus b squared, plus and so on. And you can imagine that this is the zeroth order, so it doesn't include some derivatives. So this is the order 0. This blue one is order 1 because it involves first derivative. In terms of this function of of two variables, these two terms are the order 1. And for the order 2 that involves second derivative, it is this whole part of the expansion. Okay, so if you want first order polynomial, you stop at this term. You just take this 0th order and the first order. If you want the second order, you stop at this one. Okay. Okay, so back to our question. Okay. It seems that my OneNote is lagging a little bit, so let me restart. All right. Okay. So our function is as simple as this: square root of x squared plus y squared. We want to find the first order and the second order Taylor polynomial about the point 3, 4. So what we have to do is to find the partial derivative at the point 3, 4. So let's find it. The fx is okay. This is I think it is 2x. I'm sorry, a half times x squared plus y squared to the power of minus half times 2x. So it is simply just x over square root of x squared plus y squared. And similarly for fy, it will be y over square root of x squared plus y squared. Now for fxx, okay, it is kind of complicated, but it's okay. So you can use the multiplication formula. So we just have to find the dou x of x times 1 over square root of x squared plus y squared. I think it is more simpler this way. So it is 1 times 1 over square root of x squared plus y squared plus x times the derivative of this. And it is minus half times x squared plus y squared to the power of negative 3 over 2 times 2x. So it is 1 over square root of x squared plus y squared minus x squared over x squared plus y squared to the power of minus to the power of 3 over 2. Okay. For fxy, it is more simpler because it doesn't involve y in the first derivative in terms of x. So it is simply just to the y of x over square root of x squared plus y squared. So it is x times a half times x squared plus y squared to the power of minus 3 over 2. Forgot the negative here. Times 2y. So it is simply minus xy over x squared plus y squared to the power of 3 over 2. Okay. And for fyy, it will be similar with the fxx. So it is 1 over square root of x squared plus y squared minus y squared over x squared plus y squared to the power of 3 over 2. Okay, we already find all the derivatives, and we only want these partial derivatives at the point 3, 4. So we will find, we will plug in xy equals 3, 4 in here. Let me use this red ink. So fx34 is just 3 over 5, okay? Because you know by the triple Pythagoras, square root of x squared plus y squared, if x and y is here, is simply 5. Okay. fy34 is just 4 over 5. And then fxx34 will be 1 over 5 minus, I think it is 9 over, what is it? 5 to the power of 3, I think. All right. Should be, yeah, 5 to the power of 3. So 1, 2, 5. Okay. And it will be 25. This will be 25. So it is 16 over 1 to 5. Okay. And for fxy 34, it will be minus 12 over 1 to 5. Okay. Forgot to record, so let me. Okay. Lastly, for this fyy34 will be 1 over 5 minus 16 over 1 to 5. So it will be 9 over 1 to 5. Okay, we already find all the partial derivatives. So the first order Taylor polynomial near xy equals 3, 4 is of course it will be f34 plus fx34 times x minus 3 plus fy34 times y minus 4. And it will be f34 is just 5, right, by this function. So it will be 5 plus fx is 3/5. So 3/5 times x minus 3 plus 4/5 times y minus 4. Maybe you can put you can make this polynomial. Sorry. You can make this polynomial as P1. So this first order polynomial is just like this. And for the second order, P2, you just continue from the first order like this. Plus the second order part, so it is fxx and 4/2 times x minus 3 squared plus fxy, this, plus fyy at 3/4/2 times y minus 4 squared. So it will be 5 plus, let me just copy this. Okay, and this fxx is, I believe, 16/1/5. So it will be 8/1/5 times x minus 3 squared. The fxy is minus 12. So it is minus 12/1/5 times x minus 3 y minus 4 plus the last one is 1/1/5, so it will be, let's just write it as, sorry, my OneNote is lagging again. So it will be 9/250 times y minus 4 squared. And this is the second order Taylor polynomial. And what we can do from this Taylor polynomial is actually we can find the approximation for some for the value of the function near the point 3, 4. So we notice that this is 3.1 and this is 3.9. So it is near this point. So that's why we can approximate this value with this polynomial. So this f 3.1, 3.9 will be the value of this will be about this. It will be about this first order Taylor polynomial, of course, at the same point. Also, it will be about the value of the second order Taylor polynomial. And naturally, usually it is the second order will be closer to the value of this function. Usually it is like that. So what you can do about that is just plug in the value of x equals 3.1 and y equals 3.9 in this polynomial, and you can see it will be similar with this function. Let us try it. So P1 3.1, 3.9. You can make it more easily. For this, you know the x. Sorry, the x minus 3 will be 0.1, and the y minus 4 will be minus 0.1. So from this function, you can just make this 0.1, and this is minus 0.1. It will be about 5. This will be 0.6, so 0.06. This will be 0.08. and it is 4 point, I think it is 98, right? Okay, 4.98. And for the second order, it will be like this. Let me just copy this. Okay, and just remove this by 0.1. Okay, so this is 0.1, this is negative 0.1, this is 0.1 squared. This will be negative 0.1 squared. This will be 0.1 squared. Okay, so this value will be, the first order is 4.98. For the second order, it is, let me just pull up my calculator. It is easier that way. Okay, I will just use the calculator in my phone. So 8 over 1 to 5 times 0.01. So it is 0.00064. And this is plus 0.00096. And the last one is 0.00036. So it will be, let me see, plus 0.00064 plus 0.00096 plus 0.00036. So it will be 4.98196. Okay, so this is the approximation of this of this function at the point 3.1 and 3.9. And what is the value of this function at this point? So let me pull up the calculator in this computer. So if we, okay, I don't like calculator in here, so let me just pull up the one in my phone. So the square root of 3.1 squared plus 3.9 squared, sorry. So the real value of f 3.1 comma 3.9 is actually square root of 3.1 squared plus 3.9 squared, right? And according to my calculator, it is 4.98196748828 and so on. And you can see that this value is near this first order polynomial and the second order polynomial. So the first order, so the for the first order, it is 4.98, so it stops here. And for the second order, it is more it is closer than the first order. So 4.98196 is right here. So it is closer with the real value of this function. Okay, so technically, you just have to find the partial derivatives and plug in the value of the base point, the 3/4. Okay, is that clear?
Clear, Kak. Thank you, Kak.
All right, thank you for the question. Okay, is there any other question? Anyone? Okay, if no, then let us pick another question from here. Okay, what is the interesting question here? Okay, I think the number 30 is good for our demonstration. So for number 30, we must find the maximum value of the product of three real numbers x, y, and z if those three real numbers satisfy this equation. So let us write like tx, txyz as x times y times z. So it's simply like this. And we have the constraint. It is x plus y plus z squared equals 16. So what tool do we have to use for this problem? We can solve this, hopefully, with the Lagrange multiplier. So it is nabla t equals lambda. Let me write this constraint like this: gxyz equals to x squared plus x plus y plus z squared minus 16 equals 0. So the Lagrange multiplier is nabla t equals to lambda times nabla g, and g equals 0. So for the nabla t, for the total x, it is yz equals to lambda. So I think it is easier to write it like this. So it is yz equals to lambda, because the partial derivatives in terms of x is just simply 1. For the partial derivatives in terms of y, it is xz. So xz equals to lambda again. And xy will be equal to 2 lambda times 2z. And the last one is x plus y plus z squared equals 16. So what we have to do is to solve what is the value of x, y, and z that satisfy this 4 equation. Sometimes you have to find the value of lambda, but sometimes you don't. But let us see what we can do from here. Okay, I think it is not as easy as it seems, but how do we solve this? Let's start from this two. Let me just write this as number equations like this. So from 1 and 2, we will get yz equals to xz. Okay, and maybe you can just cancel out the z, right? But you must remember that it is possible if z is not equal to 0, right? So you have to make some cases. So case 1, z is 0. If z is 0, then let me just write case 1 as z is not equal to 0. So if z is not equal to 0, then what we find is we can cancel out the z to get y equals x. Okay, so y is equal to x, and I think we can solve from the third equation. From third equation, it will be x squared equals to lambda times 2z. And for the fourth equation, it will be 2x plus z squared is equal to 16. Okay, how do we solve this? Okay. Maybe we can write this as 2x equals to 16 minus z squared. Okay, from this we can write x equals to 8 minus z squared over 2. And if we substitute to the third equation, then we will have 8 minus z squared over 2 squared equals to lambda times 2z. And yeah, I think it is complicated. I don't know if this is the right way or not. If you have any idea, let me know. Because to solve this Lagrange multiplier, there is no surefire way to do this. You just have to just try what works. From this, I don't think we can solve this easily. Let's see what we can do. I think it is easier if we make this from the third equation. This will be z equals to x squared over 2 lambda. So if we sub it into the fourth equation, then we will have 2x times x to the power of 4 over 4 lambda squared equals to 16. All right. I think this is x times 2 plus x cubed over 4 lambda squared equals 16, but I don't think we can solve for this equation. How do we solve this? Y is equals xc, that's right. Okay. Okay, maybe we can also utilize this fact that xz is equal to lambda. So remember, from the second equation, we have xz is equal to lambda. So if we use this fact into this equation, then we will have this will be z equals to x squared over 2xc. Okay, and we can cancel out the x, and we will have c squared, 2z squared is equal to x, right? 2z squared will be equal to x. I think this is the correct way. Okay, so from that we can plug in x equals 2z squared into this equation. Then we will have 4z squared plus z squared is equal to 16. Then we'll have 5z squared equals to 16. Then z squared is 16 over 5. And of course, z will be equal to 4 over square root of 5, or z will be equal to minus 4 over square root of 5. All right. So from that, we can also deduce the value of x. X is 2z squared, so it will be simply 2 times 16 over 5. So this is 32 over 5. And from our case, remember, y is equal to x. So it is 32 over 5 as well. So we have to, we found 2 points that solves the Lagrange multiplier method. It is 32 over 5, 32 over 5, and 4 over square root of 5, and 32 over 5, 32 over 5, and minus 4 over square root of 5. Okay. And we are not finished yet, because we have to consider another case, that is z equals 0. Okay, so let me copy this system of equation so we don't scroll too much. So from this, the case 2 is when z equals to 0. And if z equals to 0, then what we have from the first equation, it will be lambda is equal to 0. Okay, and from the second equation is the same. So let's just jump into the third equation. The third equation is xy will be equal to 0. And for the fourth equation, it will be x plus y plus 0 will be equal to 60. So from this, from the third equation and the fourth equation, we can also solve this. So okay, so from the third equation, we can also get two cases. So it is x equals 0 or y equals 0, right? So from this, from these cases, and we see the fourth equation, it will be y equals to 16. And for this case, it will be x equals to 16. So we find again 2 points. We found 2 points that solve this Lagrange multiplier method. It is 0, 16, 0, and it is 16, 0, 0. Okay, so and we are finished because we already consider all cases. So in summary, we found 4 points. This point, and this 2 point. And we want to find the maximizer, right? Because we want to find the maximum value. So what we have to do is just compare this the value of x times y times z in these 4 points. So let's try to find it. For the first point, it is t 32 over 5, I believe. Okay. 4 over square root of 5. So it will be 32 over 5, 32 times 32 over 5 times 4 over square root of 5. For the second point, it will be minus this product. And for the E0, 60, 0 and E16, 0, 0, it will be similar. It will be 0, okay, because it is just 0 times something. So from this, it is very clear that the maximum value is attained in this point because it is the negative value and it is 0, and this is clearly bigger than 0. So the answer is, if you have to find the maximum value, not the maximum point, right? You find the maximum value, then the answer is the max value of x, y, z that satisfies x plus y plus z squared equals 16 is 32/5 times 32/5 times 4 over square root of 5. Yeah, if you want to find the real value of this product, yeah, you can just use your calculator or just leave it as it is. Okay. It is simply like that. All right. Is there any question for this problem? There is no question, then if you have more questions from this tutorial sheets, please let me know. Okay. Okay, if there is no question, then I want to discuss a little bit for the point for the question 28 point B. I will not solve this, but I will just explain this a little bit. So as you know, if you want to find the global maximum and global minimum of the region S, so let us see first the point A. The region S is the area inside this unit circle, right? So this is the area that you have to find the maximum and the minimum of the given function. Okay, this is the region, and the visualization for that is maybe like this. Let's assume this is the unit circle. This is the inside of that unit circle. And this is the surface of z equals to fxy. And you can see that if you take this unit circle into the surface, then what you have is like the region inside this, inside that surface. And you have to find the highest point and the lowest point of this part inside of the surface. So that is your question. And how do you do that is, for the interior, you want to find the maximum and the minimum using the second derivative test. It is it the correct term? I don't know, because let me see in the book. Second partial test. It is called the second partial test in the Purcell book. So let me use the same term for that. Second partial test. Okay, it is for the interior, and for the boundary, you will use the Lagrange multiplier, of course, on x squared plus y squared equals 1. And for the interior, it is x squared plus y squared less than 1. Okay, so that is how you solve for the point A. But for the point B, you see that S is shaped like this. X is between 0 and 5, so 0 and 5. And y is between -3 and 0, so I should draw this like this. Okay. -3. Okay, so S is this region. And if you want to find the maximum and minimum value, the concept is similar. For the interior, you use the second partial test. Okay, on the blue region. So, of course, on the set of xy, where x is between 0 and 5, y is between -3 and 0, without the equal sign. But for the boundary, it is not as easy as using the Lagrange multiplier, because you can see that the boundary consists of 4 different lines, right? It is not just one singular line, one singular curve that can be described by one equation. So for the boundary, it is actually harder. So one way to solve this, let me copy this problem. So one way to solve this is to apply Lagrange multiplier 4 times on each boundary, each part of the boundary. That is, first, it is the first boundary, the left boundary, it is x equals 0, and y is from -3 to 0. The second is y, let's just use the top part, sorry. It is y equals 0, and x is from 0 to 5. The third is x equals 0, sorry, x equals 5. So it is the rightmost part of this boundary. So let me just, this is 1, 2, 3, and 4. So this is the 1, this is 2, this is 3, this is 4. So the third part is x equals 5, and y is from -3 to 0. And the fourth part is y equals to -3, and x is from 0 to 5. Okay, so you can use Lagrange multiplier 4 times on this 4 boundary. But of course, it is not as easy as saying like that, because maybe it is harder to use this Lagrange multiplier because you have to use it 4 times, and then you have to pay attention to the boundary of this. Okay, y is in between -3 and 0. So you apply the Lagrange multiplier into this boundary, x equals 0. And then if you find a point, you have to check whether the point satisfy this equation, satisfy this condition, y is between -3 to 0 or not. So it is maybe kind of hard to check that. So another way for the boundary is, if the boundary is simple like this, you can use this. So for the first boundary, that is x equals 0 and y is between -3 and 0, you can just plug in the value of x equals 0 into the function. So it is f0y is simply just y squared plus 2, right? And this function attains minimum and maximum in this condition. We can just analyze this function in this region, because this function will attain maximum when y is equal to -3, right? Because it is it will be 11, and it will attain minimum when y is equal to 0. Okay, so because we only have to find the maximum and minimum value, so the max for this boundary is 11, and the minimum for this boundary is 2. And you can check again for the second boundary. It is y equals 0 and x between 0 and 5. So this, and you just plug in y equals 0 to get fx 0. And fx 0 is x squared plus minus 6x plus 2. Okay, so this is the function, and you can again analyze when this polynomial attain maximum and minimum. And one way to do that is just to use to make this equation to be a perfect square. So remember how to make the this polynomial into the perfect square. So if you pay attention to the coefficient of the x, that is -6, you can make it plus something that makes this x squared minus 6s plus something to be the perfect square, and that is -6 over 2 squared. So it is I think 9. So this will be x squared minus 6 plus 9, and to make this expression equal, we have to subtract by 9. So again, we still have plus 2, and we must have -9, so that the value of this part is similar, is equal to the first part. So it will be x minus 3 squared minus 7. From this, we can analyze the maximum and minimum value for this function. So the maximum value is when the x is further away from 3, and the furthest point from 3 in this condition is when x equals 0, and the minimum is when the x is closer to 0 to 3. So of course it is when x equals to 3. So the maximum is when x equals 0, so it is 9 minus 7, so the maximum is 2, and the minimum is minus 7. Okay. So sometimes if you use this technique, because the boundary is simple like this, and it makes the function to be easier to analyze because it is just the second order polynomial, and you know how to analyze the second order polynomial, you can use this way to find the maximum and minimum value on the boundary. And of course, you have to continue for the third boundary and the fourth boundary. And compare and find the maximum and minimum among them. Okay, so what I want to say from this problem is sometimes not using the Lagrange multiplier is easier than using that. Okay, so it is easier to use Lagrange multiplier if the boundary is if the boundary can be expressed in one equation like this, but it will be harder if the boundary is in multiple parts like this. And sometimes if you want to use another method, it will be easier to solve this problem. Okay, so again, you just have to pay attention to the problem itself. Just you must adapt to what the problem gives you. All right, is there any question? If no, then I will finish this tutorial. I will end this tutorial. Question? Okay, then thank you very much for attending this tutorial, and I will see you guys next week. Have a good week.
Thank you, Kak.
Thank you, Kak.
Thank you, Kak.
Yes.